Okay, let's look at chapter 15. 15.1 is about quadratic inequalities, and 15.2 is about more complicated inequalities, which can be solved using methods similar to quadratic inequalities. Okay, so let's first see an example. 15.1. Find all values of x that satisfy x plus 2 times x minus 5 greater than or equal to 0. So how do we solve this inequality? So the book has a method, and I have a slightly different method, which I think is faster and easier, okay? So what we do is we first draw a number line, and then we label all the roots of the left-hand side. So this inequality, right-hand side is 0, left-hand side is in the factored form, right? So you solve the equation x plus 2, x minus 5 equals 0. You get x equals -2 or 5. Then what you do is you label the roots on the number line. So let's say this is -2 and this is 5. Okay, then you look at the two factors, for example, x plus 2 and x minus 5. These are two factors on the left-hand side, right? Then if you look at it, the x plus 2, there are 3 intervals, okay? This is interval 1, this is interval 2, this is interval 3. So none of these factors will change sign within an interval. It only changes sign from interval to another interval. Okay, so x plus 2 is going to be negative here, positive here, and positive here, right? X minus 5 is going to be negative, negative, positive. Okay, then how about the product x plus 2, x minus 5? Then we must have negative, negative give us positive. Positive, negative give us negative. Plus, plus means plus, right? So we know the sign of the left-hand side. And then, we can just label the sign above the number line. So plus, minus, plus. Okay, we are interested in the regions where this expression, this product, is greater than or equal to 0. Therefore, so 5 and -2 should be allowed, because when x is at these places, the left-hand side equals 0, right? Then we pick the positive intervals. It's like this. So the solution is using interval notation, okay, from -infinity to -2, and with -2 included. So we use square bracket. Then union from 5 to positive infinity with 5 included. So square bracket means we include that point. If we use parentheses, that means we do not include that number, okay? Okay, yeah, so this is this problem. And so, this is the first problem you solve in this, along this line, right? But, after you see a few problems, then you can speed up the process. What you can do is, you draw a number line and you label the solutions. And then what you do is you start from the rightmost interval and then determine the sign of the left-hand side in each interval from the rightmost and then move towards the left, okay? So let's say this is 1, 2, 3. So from 1 to 2, then 2 to 3. Okay, then look at this equation. The exponent of x minus 2 and x minus 5 are both 1. We call -2 and 5 simple solutions of the equation, the corresponding equation. If the exponent is bigger than 1, for example 2, then we call that solution a double solution. If the exponent is 3, we say that solution has multiplicity 3. For this case, both the solution -2 and 5 are simple solutions. So then, the coefficient of this left-hand side polynomial is 1, positive. Then what do we know? Starting from the rightmost interval, okay? Think about, because the expression will not change value within an interval. You can think of x to be a very large number, let's say a million. If x is a million, x plus 2, x minus 5 must be positive, right? Therefore, this interval, 5 to negative positive infinity, so the expression, the left-hand side polynomial, has positive values. Then you move towards the left. Every time you pass a simple root, only one, there's one and only one term in the expression is going to change sign. For example, in this case, x plus 2 will not change sign as we move across the number 5. But x minus 5 is going to change from positive to negative. So every time there's exactly one term which changes sign. So what does that mean? That means, okay, the sign in the interval from -2 to 5 is simply negative, right? You just, from plus you go to negative, minus. Then from minus you go to plus. Okay, then the same rule applies. Okay, as x moves across the point -2, then one and only one term changes sign, right? So if the expression has negative value between -2 and 5, add another minus sign, then we should have plus, right? So then you see we have alternating signs starting from the rightmost interval and moving towards the left. So plus minus plus. Okay, so this is a pattern. So in this section, almost all of the inequalities can be solved in this way. So then using this method, you can immediately write down the solution includes these two intervals, right? Okay, now let's see the next example. Problem 15.2. Find all values of r such that r squared minus 8r less than -12. So in order to solve this inequality, we can't just factor r, factor the left-hand side, because the right-hand side is not 0. So what we can do is we move the right-hand side to the left-hand side, then change the sign. So r squared minus 8r plus 12 less than 0. This is a strict inequality. Okay. Then we need to factor the left-hand side. So what is it? So it's r minus 2 times r minus 6 less than 0, right? So the inequality becomes like this. So there are two factors. One is r minus 2, one is r minus 6. And both have simplicity 1. So the exponent is 1. So then using the method we introduced through the last example, okay, we know there are two roots, right? 2 and 6. Then we determine the sign of the left-hand side within each interval. And again, we start from the rightmost one because the coefficients of the polynomial is positive, okay? Then when r is very big, we have a positive number, so plus. Then you see, every root is simple. You just do plus minus plus without even thinking. Okay, so then you see, now we are interested in when the inequality is less than 0. So we cannot include the point 2 and 6. I'm just going to draw a circle over there, meaning these 2 points are excluded, okay? So the solution is this interval. The solution is from 2 to 6. So x less than 6, bigger than 2. Or using interval notation is parentheses from 2 to 6. So parentheses means the boundary points not included. Okay, and this means inside, belong to. Let's look at the next example. Problem 15.3. Now, consider the inequality x squared minus 6x plus 13 less than or equal to 0. Part A, what are the roots of the quadratic? Okay, first look at the roots. X squared minus 6x plus 13 equals 0. So, I don't know how to factor this, but if you're familiar with quadratic equations, you must know this, right? X squared minus 6x plus 9. This is nothing else but x minus 3 squared, right? And then you need to add 4 equals 0. So x minus 3 squared plus 4 equals 0. There's no real solution, right? There are complex conjugate solutions, but there's no real solution. And this quantity, if x is a real number, then x minus 3 squared plus 4 is always bigger than 0, right? So what does it mean? The inequality has no solution. I mean, if x is a complex number, we cannot compare complex numbers with 0, so it doesn't apply here. Okay, so this is based on our experience. Second, B. Graph the equation y squared, y equals x squared minus 6x plus 13. How do we graph this equation? And you can write it. Again, you can complete the squares, right? Then the graph just looks like this. X-axis, y-axis, origin, and it's a parabola. When x equals 3, y equals 4. So it passes this point, opens up, and it's a parabola like this. Then you can see there's no intersection point with the x-axis, and there's no, so the whole curve is above the x-axis. Therefore, there's no solution to the inequality. Now, let's look at part C. Explain how your graph from part B can be used to explain why the inequality has no solutions. Well, yeah, well, everything is above, so there's no solution. We already did that. Part D, what real values of x satisfy x squared minus 6x plus 13 bigger than 0? The other side, right? So this is always true, right? All real numbers. Okay, R stands for all real numbers. Now, let's look at problem 15.4. Graph the inequality y is bigger than 2x squared plus x minus 3. Okay, so how do we graph this inequality? So there are two variables. One variable is y, one variable is x. Now, let's look at the equation, the corresponding equation instead. Y equals 2x squared plus x minus 3. The right-hand side is a quadratic equation, right? And the curve is called a parabola. Okay, then Oh, there is an 8, sorry. Okay, then what do? We can do many things, right? How about we complete the square? 2 times x squared plus 4x. Then if we add 4, that would be awesome, right? This is x plus 2 squared. Then we add 4, that means we add 8. We need to subtract 8 in order to get y, right? Yeah. So this is 2 times x plus 2 squared minus 11. Now, if you graph this curve, what do you get? X, Y, 0. When x equals -2, y equals -11. Let me move this in this direction a little bit so it's easier to plot. So y equals -11. Let's say this is -11. Okay. Okay, then you can draw the curve, right? Yeah. So this is the equation, the equation. Now we want to plot the inequality. Now on the curve, we have y equals this quantity. So for y bigger than that quantity, it must be above this curve, right? Yeah. Okay. So homework for this section is just the exercises. 15.1.1 to 15.1.5. The last problem is a challenge problem, okay? But I think you guys will get it. And yeah, only 5 problems. Okay, now let's look at section 15.2. Beyond quadratics. Okay, beyond quadratics. Problem 15.5. Solve the inequality 2x minus 1, x plus 1, x plus 7 bigger than 0. Okay, so what I'm going to do is I will take this 2 out, okay? I write it as 2 times x minus a half, x plus 1, and x plus 7. Then this polynomial is bigger than 0. This is the equation we have, right? So what are the roots? I mean, the inequality we have, the corresponding equation have 3 roots, and x equals a half, x equals -1, x equals -7, and all of them are simple roots. Okay, so what I'm going to do is I'm going to label these roots on the number line. I don't need to be super accurate. I just need to know the order of them, okay? So let's say this is -7, this is -1, and this is 1/2, okay? So this divides the number line to 4 intervals. And the polynomial on the left-hand side can have different signs in each interval, but they will not change sign within each interval. Then we just determine the sign of the polynomial in each interval, right? Okay, remember we said when x is very large, think about a million, then this rightmost interval must be positive, so plus. Now, as x becomes smaller than a half, okay, only this factor is going to change sign. The other 2 factors, the sign of the other 2 factors will not be affected, although their magnitude changes, right? But the sign will not change. So we gain 1 negative, so this interval must be negative. And as x becomes even smaller, okay, now belong to the interval 3. Then one more term changes sign. So x plus 1 changes sign, right? So we must have plus here. Okay, now x becomes even smaller, then x plus 7 is going to change sign. So we have a negative here. Now, you labeled the sign in each interval. You can immediately write down the solution to this inequality. So because we have strict inequality, so all these rules cannot be included. So I draw 3 circles, meaning excluding these points. And I'm interested in intervals where the left-hand side is positive. So I'm interested in the plus intervals. So I have 2 of them, right? Then based on this analysis, I can write down the solutions. Okay, for example, using interval notation, it's going to be -7 to -1. Union. So union is a set operation. If you have 2 subsets, you can join them together to form a bigger set. And union a half to positive infinity. What does this mean? It means x less than 1, bigger than -7, or x bigger than a half. Okay, got it? Now let's look at problem 15.6. So higher order polynomial equation is not the only one that this method works. It also works for rational functions, rational inequality. Let's look at this one. X plus 3, 1 minus x divided by x minus 5, bigger than or equal to 0. Okay, first of all, I'm going to rewrite this inequality a little bit. I want every factor have the form x minus something or x plus something, okay? And this one, this term is 1 minus x. So I'm going to multiply by -1 on both sides. So what I get is x plus 3, x minus 1, x minus 5, less than or equal to 0. This step is not necessary, but it helps prevent mistakes. Then you see, now the left-hand side quantity, whether it's positive or negative or 0, depends on what? Depends on the sign of these 3 binomials, right? These 3 terms, okay? Then again, we draw a number line, okay? Then when x plus 3 can be 0 when x equals -3. X minus 1 can be 0 when x equals 1. X minus 5 cannot be 0. So when x equals 5 is not defined, right? So we have to exclude the point 5. So I'm going to draw a circle over there. That means this point cannot be considered. Okay, the x minus 5 will change sign when, as x moves across 5, right? So I labeled these 3 roots of the 3 terms. Okay, then what I do, the sign of the left-hand side, I'm going to call it, this is a rational function. So I'm going to call the left-hand side R, okay? So the sign of R depends on the sign of these 3 terms. Well, x is bigger than 5. When x is a million, for example, all 3 terms are going to be positive. So I have plus sign here. Then as x moves to be smaller than 5, and in the interval 1 to 5, then only one term is going to change sign, which is x minus 5. So we have a negative here, right? So this is 3, this is 4. And then you continue this process. All the terms have exponent 1, so you just plus minus, you just have alternating signs. Then, okay, now you are interested in r less than or equal to 0, right? So it can be 0. So, for the point, -3 and 1 should be included. And we need negative intervals. So here and here, right? So what is the solution? The solution is -infinity to -3 union, okay, square bracket. because -3 needs to be included, and square bracket for 1. So 1 to 5, and 5, this needs to be a parenthesis because x equals 5. When x equals 5, the inequality is not defined. Now let's look at problem 15.7. Solve the inequality 2 over x minus 2 minus 2 over x plus 3 bigger than -1. For this inequality, we do not have a super nice form where the right-hand side is just 0 and the left-hand side is a fraction with numerator and denominator in the factored form. And then for this kind of problem, we need to do some preparation before we solve it. So first, we are going to move all the terms to the left-hand side. So that means we add 1 to both sides. And then we are going to write the left-hand side as a single fraction. And the common denominator is x minus 2 times x plus 3. The numerator, we have 2 times x plus 3 minus 2 times x minus 2 plus x minus 2, x plus 3, right? Bigger than 0. Now let's look at the numerator. We can simplify it as 2x plus 6 minus 2x plus 4 plus x squared plus x minus 6, right? So what is this? So 2x cancels. 6 cancels. We have x squared plus x plus 4. For this quadratic, if you're familiar with completing the squares and quadratics, you realize that this is x squared plus x plus 1/4, then plus 15 over 4, right? And this is x plus 1/2 squared. So the whole thing is going to be positive all the time. Okay, so that means the numerator is always positive. So the magnitude, we are solving an inequality, so it doesn't really matter anymore. So for this inequality, we know something positive divided by x minus 2 times x plus 3. And we want this to be positive, right? So all we need to do is to look at the sign of these two factors. And there are two roots of these two factors. One is -3 and one is 2. So when x is bigger than 2, both of them are positive. So we have plus. Again, the signs alternate, plus, minus, plus, right? So we are interested in regions where this quantity is positive. And of course, we cannot have -3 and 2 because these factors appear in the denominator. We have to exclude these 2 points. So the solution is going to be these two intervals. So x belongs to -infinity to -3, union parentheses 2 to positive infinity. Homework for this section, 15.2.1 to 15.2.4.